One of the biggest challenges in science is making sure that we're all talking about the same thing. Otherwise, when we start having conversations about stuff in chemistry, if you're missing the basic terminology, you can fake your way through for a little bit. But at some time, the terminology is going to become a barrier to understanding what it is we're actually talking about. We have 3 pairs of words that are very similar to each other but distinctly different. And we need to start using the language of science better so that we don't confuse ourselves. Elements versus atoms. Anybody want to start us off? There's 118 elements. Periodic table of elements. What is an element? So if I say we have gold versus iron, does that matter to you? No? So if I'm selling you stocks in gold or iron, what are you going to buy?
Gold.
Why?
It's more expensive.
And?
Prices are most likely to go up with it too.
You can tell when the U.S. economy is going through a troubling part or investors are getting really scared. Watch gold prices on the TSX market or on the Dow. Because when investors start getting nervous, they invest in gold. Because it's more stable, it holds its price over a longer time. These are the building blocks that have a particular identity. We can start putting those building blocks together to use an analogy like Lego. And we can build very, very large structures. For example, the molecule that makes you, DNA, is made up of millions of elements that have come together. I say that I have an atom of gold. That's a little bit different. It's still a building block. When we learned Dalton's theory in Science 9, we learned that everything is made up of atoms. What makes an atom different than an element? Every atom is made up of 3 basic subatomic particles. What are your 3 particles?
Protons, neutrons,
Awesome. Do you remember how to find out the number of protons and electrons of an atom? Take out your periodic table. Find carbon. I'll give you a hint. It's on the right-hand side of the periodic table, closest to the top.
Look at its atomic number.
Here is carbon right here. What number is it? 6. This is called its atomic number, and it also reports the number of protons. Carbon has 6 protons. How many protons does oxygen have? 8 protons. Now, by definition, an atom must always be neutral. If it has 8 positive charges, how many negative charges is it going to have? 8. If it has 6 positive charges, how many negative charges does it have to have? 6. Okay. So, instead of writing 6 again, sorry about that. This is why there should be a weekend in between semesters. Carbon has 6 positive charges and 6 negative charges. Oxygen has 8 positive charges, 8 negative charges. We also have neutrons, which are neutral. They have no charge, but they do have mass. What is the atomic mass of carbon?
10.81.
All right, so 12.01, round that to the nearest whole number. 12 minus the number of protons, which is 6, gives carbon 6 neutrons. What is the mass for oxygen?
16.
Okay, it is 16. It's the number on the bottom here. We round that to the nearest whole number, which is 16. Subtract the number of protons, and that gives 8 electrons. So when we talk about an atom, we're talking about a structure. What does it actually physically look like? There's different ways we can model this. Do you remember looking at Bohr models in Science 9 that look like the solar system? Kind of, sort of. So for example, carbon, there's your nucleus. And then in the first orbit, you would have 2 electrons. And then the second orbit, you would have 4 electrons. So when we talk about an atom, we're thinking, what does it look like? What is it made up of? The stuff that makes up an atom directly impacts its characteristics. Oxygen is a gas at room temperature. Carbon is not. Oxygen is very highly reactive, extremely flammable. Carbon is not. In fact, if you put carbon under enough pressure for a really, really long time, you get a sparkly object known as a diamond. If you try to put oxygen gas under high pressure for a really long time, boom, not good. Especially if it's heated enough, right? You have to be really careful when pressurizing oxygen into something like a tank. So an atom is structure. An element is what something is because of what it's made up of. One is tied into the other, but not the same thing. For this one, I'm going to switch to the picture that you have here. In this model, what represents atoms? Each individual shape represents an atom. For example, this circle here represents an atom. This triangle represents an atom. The square by itself is an atom. It gives you 3 examples of molecules on this picture. Right here, and right here. What is a molecule? Felton?
A chemical bond between 2 atoms.
Okay, a molecule is when something is made up of 2 or more atoms. So all of these things here, which have at least 2 things, 2 shapes connected together, those are all molecules. And not all of them are compounds. If we go back to the original 3 things that were circled, only this one and this one are compounds. This is not a compound. All compounds are molecules, but not all molecules are compounds. What is the difference between a molecule and a compound? What's the key word, Dana? Different atoms. That means that a compound must have 2 different symbols or 2 different shapes to be classified as a compound. An example. This is in your salt shaker, and it is made up of 1 part sodium and 1 part chlorine. We call it salt. Chemistry calls this sodium chloride. This molecule that you breathe is not a compound. It is made up of 2 atoms. It has 2 parts oxygen, but those 2 parts are identical to each other. It's not a compound. This one is a hard one for people to keep straight because we mess it up all the time in everyday language. The reason is it can be a state. For example, solid, liquid, gas. But it can also be used to indicate the state of a pure substance. So oftentimes, I have got my liquid gold here, well, liquid dark, right? All right, so if I pour stuff and it does not retain its shape, it's a liquid. This is a fluid. Now, actually, technically, coffee is a solution. So liquid can indicate state. But in chem, it is the state of a pure substance. And as much as I'd like to think coffee is pure caffeine, it's not. I'm gonna live dangerously and see how long it takes to fall off the table, right? Coffee is a mixture of water and I think about 200 different types of compounds within that give it its taste, its smell. If you've ever tried coffee from different regions of the world, it will taste differently because there's different compounds that it absorbs from the soil. When we talk about a solution is a mixture with water being the most common thing that mixture is with. For example, when you were announcing chemical reactions yesterday, you noticed letters behind those compound formulas. Those letters indicate something about that compound. But do you know the difference is between NaCl with an L behind it and NaCl with an AQ behind it? NaCl is only salt, and it is in a liquid state. We say molten sodium chloride because it has to be darn hot to get those salt crystals to melt. We can drink this, NaClAQ. You're definitely not pouring liquid molten sodium chloride down your throat. You won't have a throat if you try to drink molten salt. And by the way, this is not the Tide Challenge Part 2. Okay. If it is NaClAQ, that means aqueous, aqua,
Water.
yep. That means that the salt has been dissolved into water. This is a handy trick if you have a sore throat. You mix about a teaspoon of salt with warm water and then you gargle it to try to kill the bacteria that's in your throat. Or if you are James Bond Part 2 and you consume poisoned martini and you need to make yourself puke, you put a whole lot of salt in water and that makes things come up. So yeah, I just taught you how to save your life if you become a super spy. So liquid means something different than solution, but it's really challenging because we don't talk about it this way in real life once you leave this classroom. One of the things that the class overwhelmingly said that they wanted help with was molecular compounds versus ionic compounds.
How is it possible that only 92 elements are found in the natural world, but there are millions of different types of substances? The secret is that atoms combine into compounds, which provide the great variety of chemical structures that make up the different substances we find in the universe. Compounds are made up of combinations of atoms. When atoms bump into each other, the electric charges of the nucleus and the electrons of one are felt by the other. This is the electromagnetic force that binds atoms together. The way they do that is by sharing or donating the electrons in their outer shells.
That is the key.
There is a natural tendency for atoms to seek equal.
is the key thing about how substances form compounds. It actually has to do with electrons. If electrons are given up by one thing and taken by another, we get the formation of ionic compounds. If we have two or more things that share electrons, that is a covalent compound.
Equilibrium and fill their shells with electrons, and they do this by combining with other atoms. The more full the outer shell of the atom, the greater its stability. An ionic compound is formed when an electron from one atom is lost to another, and the two ions form an ionic bond. They are held together by their opposite electrical charges, but they remain as individual ions. A molecular compound, on the other hand, forms when atoms share some of their electrons in a covalent bond. Oxygen, for example, has 8 electrons. In order to become stable and have a complete outer shell, it needs another 2 electrons. Hydrogen has only 1 electron, but when 2 hydrogen atoms combine with an oxygen atom, the 3 atoms in the molecule.
Think about other words that start with co. What other words start with co? Main gas station between here in Yorkton and Kenora, on the south side of Kenora now.
Co-op,
The co-op. What is a co-op?
cooperation.
Okay, what is it? Can you describe it without using the word co-op? Can anybody use a co-op? Absolutely they can, right? So, but if I want to get the benefits from it, I have to buy a membership, right? Because the whole idea of cooperative is to get a group of people together to share responsibility financially. Technically, in a cooperative, if it loses money, I have to pay my fair share of that debt. So they deliberately structure it so that they have a profit, and then once a year there's an equity day, and I get my share of the profit. So co means to share. Valence is the electrons that are in the last level of an orbit. Hydrogen only has one orbit, so it's automatically the last one. With oxygen, here, these electrons here are the ones that are going to be shared. Any suggestions why it's the last set of electrons that are being shared? What do you think holds electrons to an atom? Electrons are negative. What holds them to oxygen? What's in the middle? Now, what's in the nucleus? In the nucleus, you have your protons and your neutrons. Protons have a...
Positive charge.
Oh, what happens when you get positive charges next to negative charges? They attract, right? So, why do you think we can do things with these electrons that are out here, but we can't do the same things with these electrons that are closer to the center?
Because the outside ones leave or connect more freely than the inside.
Absolutely, they travel more freely because they're further away. There's less attraction to the center. So really interesting things can happen with those electrons. Absolutely. So when we talk about atomic structure, things like that affect how that atom can connect with other things. That's why structure has such a big impact on the characteristics of a substance.
Will share electrons in order to fill their outer shells. Two atoms of hydrogen and one of oxygen is a molecule of water, H2O, one of the most common and stable substances on our planet. In some instances, two atoms of the same element combine. Oxygen in the atmosphere exists as a molecule of two oxygen atoms, O2. Hydrogen is often found as a molecule of two hydrogen atoms, H2. When atoms combine, the resulting molecules can take on a character much different from their constituent elements. Hydrogen is highly explosive, and oxygen burns. But put together, they create water, which puts out fire. One of the marvels of modern chemistry is that scientists have even been able to create new molecular structures, such as plastic. Chemists have learned to manipulate the molecular structures of petroleum to create products with the exact characteristics they want. Not only have chemists learned to analyze the properties of molecules, but they have also developed their own way to describe them. Every chemist knows that H2 means that the molecule has two hydrogen atoms. The formula for butane, a highly flammable gas, is written C4H10. The molecule in this compound is made up of 4 carbon atoms and 10 hydrogen atoms. These types of formulas are an international shorthand that can be understood by everyone once they know the symbols for the elements.
So we know that a compound needs more than one element. There's an infinite number of compounds that we can naturally and artificially create. We use formulas to indicate the ratio of elements that exist within a substance. When we write symbols, it is really important that we properly use capital or lowercase letters. Every time you use a capital letter, you are indicating a new element. If the formula is CS2, capital C indicates that this is carbon, capital S indicates that the next thing is sulfur. It is possible to have capital C lowercase s. This is cesium. Letter size makes a difference. If you're worried that your handwriting is going to get you into trouble, sometimes what people do is the lowercase is written in cursive. For example, this. And that way, if they're writing fast and it ends up looking like this, I know that the second letter is actually a lowercase letter. This is what we call a subscript. Subscript goes to the right and below. So, think submarine underneath the water, right? If you have a superscript, which is going to be something like ion charge, Superman. Okay, so superscript goes above, subscript goes below. Sometimes you have to trick your brain into knowing those little things to help you keep the difference. The subscript tells you the number. Okay, that symbol is not a hashtag. It means number. That submarine is actually pretty bad. Okay. Sorry. Thought I erased all the slides here. So we'll do this first. I was recording another video and I wrote on it and I forgot to take all my writing off. As it was mentioned previously, compounds are formed when substances either give up their electrons to something else or if they share. Valence refers to those electrons that are further away and in the outer energy level of an atomic model. For example, if we have carbon, we have 2 electrons in the first energy level. We have 4 electrons in the second energy level. The second energy level is the valence level for carbon, and it's those 4 electrons that are going to be involved with creating compounds. The inner 2 electrons are too close, and the attraction between the protons and the electrons is very, very hard to disrupt. Ionic compounds are made from ions. We have 2 categories of ions. A cation, which is a positive charge. I remember that because the T reminds me of the positive symbol. The negative ion is called an anion, not an onion. And that is a negative charge. Lots of N's in that word compared to the word cation. Please find sodium. What is sodium's number? 11. That means that it has 11 protons. The atomic number is always the number of protons. The sodium ion also has 11 protons. What changes is the number of electrons. The atom, by definition, is neutral. That means if it has 11 protons, it must have 11 electrons. Protons are positive, so if I have positive 11 plus negative 11, and I add up those charges overall, I get 0. Metals tend to lose their electrons, especially in groups 1 and 2, the alkali metals and the alkaline earth metals here. And when they lose electrons, they become positively charged. How is it possible that if something loses an electron, its charge is positive? So the sodium ion only has 10 electrons. If I add up the number of positive charges and the number of negative charges, what do I get? Yes, exactly. So positive 11 plus negative 10 Wow, this tells me that I have one less electron than proton. Look at sodium again on your periodic table. Go into the top right-hand corner. Aha! This is an ion charge. If we want to make ionic compounds using sodium, we must use that piece of information that is given to us on the periodic table. Super important numbers. Isn't it scary when you start to understand Miss Patterson's sense of humor? Oh no! I think I'm going to have to create 2 different smartboard files. One for when I do online recording sessions and one for you so that I remember to erase things. Non-metals. Oh, what's a non-metal? You've got to stop me when you don't know what a word is, okay?
Something that's not metal.
Shouldn't have spilled my coffee all over the table, hey? How do you know on the periodic table where the metals are and where the non-metals are? Yes, the staircase line. And guess what? It's not on your periodic table. Oh, it's so mean, right? If you get lost, look at examples on the periodic table. Is oxygen something that we think of as being metallic? No. But if you look at things like iron or silver, or perhaps down here, gold, oh, no, those things are metallic. The staircase line starts off here between boron and aluminum. It goes down in between aluminum and silicon. Then it goes over between silicon and germanium. It goes in between germanium and arsenic. It goes across in between arsenic and antimony. It goes down in between antimony and tellurium. It goes across in between tellurium and polonium. And in between polonium and astatine. It is hypothesized that it might continue on. However, one of the challenges of researching the elements that are above number 92 on the periodic table is that they're synthetic. It's really hard and expensive to make these things. And a lot of the things in this 7th row of the periodic table exist for such a short period of time. We actually don't know how they behave with other things. When I say that they exist for a short period of time, I'm thinking milliseconds.
Is bottom two, or
So
does
in
it go straight
between,
down?
we don't know where it's going to go after this.
Oh, so those are non-metals, or those are metals?
I would not ask you to classify 116, 117, 118 as metal or non-metal.
They're just
Not,
medium.
we don't actually even work with them in compound formulas at all because we don't have a great understanding of how they interact. We have a lot of hypotheses. Now, I'm warning you that statement could change drastically over the next 5 or 6 months. It's actually getting really hard to keep up with the new physics and chemistry stuff that's coming out. First of all, because we're learning so much so fast, and second of all, you need like 3 or 4 degrees to understand what they're saying. So it gets a little bit challenging sometimes. Find chlorine. Find Cl on your table. All right, 17. The chlorine atom has 17 positive charges. The chlorine ion also has 17 positive charges. An atom, by definition, is neutral. That means that there must be 17 electrons in a chlorine atom. Look in the top right-hand corner of the chlorine box. What is its charge? All right. If the charge of chlorine is 1 negative, and we know it has 17 positive charges, how many electrons must it have? 18. Here's another way to think about it. If I have 17 positive charges, I don't know what my negative charges are, but I know the overall charge has to be -1. I can use the math stuff to figure out what x is. How am I going to figure out x? What you do to one side, you must do to another. -1 minus 17 is going to be -18. Those charges in the right-hand corner are going to be how you decide the ratio of metal ions or cations to anions. Take a look at iron, number 26 on the periodic table. Oh. There's 2 different charges. Oh, not positive 13, positive 3. Wow. I'm sorry, I'm really tired. We know that iron has to have 26 positive charges. If we change the number of protons, it becomes a totally different substance. All right? So your challenge for the weekend is to figure out how many electrons in each. Have a great weekend. Enjoy the Mushers Rendezvous. Get some sleep. I'll see you on Monday.